Okay, so I'm going to start with number 3, just because I think it's easier than number 1. And also it's similar to a problem that was in the daily video. So they're saying that this is the Maxwell-Boltzmann distribution curve for a sample of nitrogen at 25 degrees. And they want to know what would a similar curve look like for a sample of oxygen at 25 degrees. And I don't really know why they've got this thing hanging up here like this. Usually these curves, come down. But be that as it may. So, since they are both at the same temperature, what we're looking at here is not a matter of kinetic energy. These two molecules are going to move at different speeds because they have different masses. And if you remember, the light guys move faster, the heavy guys move slower. Nitrogen has a molar mass of 28 grams per mole. Oxygen is 32 grams per mole. So oxygen's a little bit heavier than nitrogen. That means it's going to be a little bit slower. Look at our possible answers. We're looking at which one has a curve that represents a slower gas. And remember, the x-axis here is speed, and these x-axes go from slow to fast. So even though it is somewhat counterintuitive, this high peak over here represents the slower, heavier oxygen. So keep that in mind. On the left is slow. As they get faster, the curve is flattening out more and going over to the right. Okay, take a look now back at number 1, which is the same question really, but just with a lot more words and a lot harder to understand. Again, they're telling us this is 4 different gases and they're all at the same temperature. So the thing that is making these 4 gases, some of them slower, some of them faster, are their different molar masses. That's the only thing that will impact the velocity of a gas particle. And so if you just glance through these possible answers, down here at the bottom, you see a formula that is given to you on the formula sheet, kinetic energy, and you'll notice it has down here AVG. So average kinetic energy is 1/2 mass times velocity squared. So this is that same thing we keep running into in any physical science class. If you have 2 variables that are on the same side of the equal sign, they're inversely related. So higher mass means lower velocity and vice versa. That is assuming that kinetic energy is held constant. The other thing that can impact speed, if the mass is staying the same, so you're talking about the same gas, if you raise the temperature, yes, the velocity is going to increase. If you lower the temperature, it will go slower. But here, they're all at the same temperature, so light guys move faster, heavy guys move slower, and it's really important and kind of hard to remember that x-axis on these things goes from slow to fast. So this guy right here is the fast one. This guy over here is the slow one. And answer D is correct. The molecular masses of the gases, because the gas molecule is having the same average kinetic energy, same temperature, mass can be calculated using this equation. We're not going to do it. We never actually do math with that, but we could. Okay. Question 2 is a similar question. I've got 2 different samples of gas. I've got a 1-liter sample of helium gas at 1 atmosphere and 25 degrees C, a 1-liter sample of neon gas at 1 atmosphere and 25 degrees C. I'm going to mix the 2 together. Note, temperature is kept constant. So which of these statements is true? A and B are talking about the speeds changing. C says the average kinetic energy of the helium atoms increase when the gases are combined. Well, the temperature stays constant. So average kinetic energy is staying constant. The speeds are not going to change for helium or for neon because they're still at the same temperature. They still have the same molar mass, each one of them individually. They're going to continue to have the same average speed. The answer here is D. The average kinetic energy of the helium atoms and the neon atoms do not change when the gases are combined. Okay? Let's take a look at number 4. Here, we're talking about a single gas at 2 different temperatures. So the thing that is making the difference in slow versus fast is difference in temperature. Higher temperature is going to mean faster. Over here, because speed is slow, going from slow to fast, this is the faster, hotter gas. And over here, this is the slower, cooler gas. So which one of these statements says that? If you read through anything, through all these options, A says the speed at T1 is greater than T2. No, that doesn't say what the x-axis says. B says the taller peak corresponds to the higher temperature. You know, that is so enticing because that high peak looks fast, but it's not. It's slow. C talks about there being different numbers of molecules. These things look like they have the same area under the curve. The curve is different shape, but they have the same area, same number of molecules of gas. The answer here, again, is D. The average kinetic energy of the molecules is greater at T2 than at T1. That's why it's faster. Okay, now we're back to another question down here that's going to be about molar mass. The temperature is the same, 300 Kelvin for both of these gases. This is oxygen, so what could this curve represent? Well, this curve over here on the left is slower, therefore it is heavier. That says heavier. The only one of these answers that has a higher molar mass than oxygen is bromine. Boop, boop. Okay, check out the next video in a few minutes.